All right, if we want to graph f of x equals 1 over x squared minus 1, going over the steps in class, right, we have first domain, intercepts, symmetry, asymptotes, intervals of increase, decrease, local extrema, and the values, concavity, and then sketch the curve. So the first thing we're going to do is talk about domain. For this, the only things that would make the function bad are possible zeros in the denominator. And so what we're going to do is see where the denominator is equal to 0, and then we need to restrict those. So if we set x squared minus 1 equals 0, that's going to leave us with, x squared equals 1, so x equals plus or minus 1. Or you could have factored it out, x plus 1, x minus 1 equals 0, x equals plus or minus 1, right? Either way. But anyway, those are the points where the denominator is equal to 0. So those need to be restricted from our domain. There are no other values that are going to make this function non-existent because we don't have any even roots or any logs or anything like that. So let's go ahead and write our domain as from negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Okay, so that's our domain. So that one is taken care of. The next thing we do is intercepts, right? So let's go ahead and write down the intercepts. Whenever we solve for the intercepts, to see where the x-intercepts and then y-intercept is we set y equal to 0 and solve for x. And here we set x equal to 0 and solve for y. All right? And so for this, we have, and y is just the same as f of x, right? So we have 0 equals 1 over x squared minus 1. Well, where is 1 over x squared minus 1 equal to 0? Well, that's never going to be the case. So here, let's just put never. And then over here, we set x equal to 0 and solve for y. So we get that y is equal to 1 over 0 squared minus 1, which is just equal to negative 1, right? And so my y-intercept is going to be, x was 0, right? So it's 0 comma negative 1. Okay? So I'm going to erase the work, and I'm just going to put down no x-intercepts. Y-intercept is at 0, negative 1. Okay, so that's dealing with all of the intercepts. Now I look at symmetry. So first of all, we can base our symmetry a little bit on the domain. So if I had the domain go from negative infinity to negative 1, union negative 1 to like 5, union 5 to infinity, I would know that there's not going to be any symmetry. But based on this, the fact that from 0 I go over to negative 1 and over to 1, there possibly is symmetry. It could be even, could be odd, right? And so in order to determine symmetry, what we do is with our original function, we replace that x with a negative x and then follow that through all the way to see if f of negative x is equal to f of x, or if f of negative x is equal to negative f of x, and that will give us even or odd respectively. So here we go. F of negative x is equal to 1 over negative x squared minus 1. But again, negative x quantity squared is just x squared, so this is 1 over x squared minus 1. So this is the exact same thing that f of x was equal to. So I'm given that f of negative x equals f of x, therefore f is even and therefore symmetric about the y-axis. Okay? So I have that about symmetry. What that means is, as of this point, we don't have to look at the entire number line from negative infinity to infinity. We can just focus on half of that, let's say from 0 to infinity, or if you want to be negative, you go from negative infinity to 0. I'm a positive person, we're going to go and do the positive part of that. But this gives us that information where we can only focus on half. So that symmetry, that's done. I now know that my function is going to be symmetric about the y-axis. Asymptotes. Okay, so there are two types of asymptotes, or possible types of asymptotes that we focus on, and those are vertical asymptotes and horizontal asymptotes. There are also oblique asymptotes or slant asymptotes. We don't really focus on those here. So let's focus first on vertical asymptotes. Okay, vertical asymptotes could only possibly exist at values not in the domain of the function. Okay, so because we're only focusing on the positives, because we had that the function is symmetric about the y-axis, let's go ahead and look at x equals 1, because on the positives, that's the only value that is not in the domain of the function. So I'm going to take the limit as x approaches 1 from the left, and I'm also going to take the limit as x approaches 1 from the right to see what we have. So when I do this, right, I try using just direct substitution, and what I get is I get 1 divided by 0. Now 1 divided by 0, remember, is not a terrible thing. That tells me that it's going to go to one of the infinities. So I don't know what infinity it's going to go to. So let's check that out. So if I plug in something very close to 1, but slightly less than it, like 0.999, right? I do that, I square it, and I subtract 1. Whatever I have here that's less than 1, 0.999 or whatever, is going to be, even when I square it, less than 1. So the whole denominator is going to be negative. 1 divided by something that's approaching 0 but is always negative would mean that this goes to negative infinity. Okay? And then over here, if I take something that is approaching 1, but in a positive direction, so meaning 1.001 or something like that, I take that and I plug it in for x. I square that. That's still close to 1, but slightly bigger than 1. I subtract 1. That's going to 0, but is always positive. 1 over something that's going to 0, but always positive would mean that this goes to positive infinity, and therefore does not exist. Now, with this information, I then have to finish by saying, therefore, there exists a vertical asymptote at x equals, and now this gave us 1, but due to symmetry, I know it's also going to be negative 1. So I'm going to say plus or minus 1. Okay? And then I am going to box that. Okay, so that's what we do for vertical asymptotes. For horizontal asymptotes, we look at the limit as x approaches infinity and the limit as x approaches negative infinity. Again, due to the nature of this problem and the fact that it's symmetric about the y-axis, I only have to focus on one of those, and then the other is going to be the same. So if I look at the limit as x approaches positive infinity of this guy, as x is approaching infinity, the denominator is getting infinitely large while the numerator is only going to be 1. So 1 over something that gets very, very, very large goes to 0. Again, the limit statement is not enough. I need to say what that means. So I'm going to say, therefore, there exists a horizontal asymptote at y equals 0. And because it's at y equals 0 on that side, it's also going to be for negative infinity as well. So there's only one horizontal asymptote. Okay? Okay, so now I've done asymptotes as well. So as a quick view of what we have so far, let's go ahead and erase all this. Seeing what that means for us and our graph. So we know already, just based on what we've done, first of all, that the domain we have 1 and we have negative 1, so just based on our domain, we know that the function does not exist at x equals -1 or x equals 1. There are no x-intercepts, but there is a y-intercept at 0, -1. So that is there. I know that it's symmetric about the y-axis. I can't really put that down yet in terms of the graph of it because I don't have any other points other than what is on the y-axis. But then I do know that as x approaches 1 from the left, I have that the function is approaching -infinity. So I know that there is a vertical asymptote here. And this is approaching -infinity. I also know that as I approach 1 from the right, based on my work, that the function approaches +infinity. So I don't know exactly how it approaches it or what, but I just know that it goes to +infinity on that side. Okay? Now, based on the fact that the function is symmetric about the y-axis, what that means is there is also a vertical asymptote at x equals -1. And think about the mirror image of this. That would mean that this function is approaching -infinity as you approach -1 from the right, and the function is going to approach +infinity as you approach -1 from the left. So I'm going to put that down there as well. Now, I don't really know what's going on here. This could, do other things right here. I've connected them, but I'm not sure. But the one thing I do know is that the function will not cross the x-axis, because then we would have gotten an x-intercept, but we already determined that there are no x-intercepts for this function. Okay? All right, so this is what I have so far. So I've done domain, intercepts, symmetry, and asymptotes. So the next thing that I'm going to do, which is really the first time that we're going to use a derivative on this problem, is we're going to go through and we're going to talk about intervals of increase, decrease. So again, I had that my function is 1 over x squared minus 1. So in order to talk about intervals of increase, decrease, I need to find the derivative. And so when we do that, depending on how you think of this, some people might call this x squared minus 1 to the -1st power. Some people might leave it like that and use a quotient rule. I tend to think about it like this. So let's go ahead and use that. So f prime of x is equal to negative x squared minus 1 to the -2nd times 2x, okay? Which could be simplified down to -2x over x squared minus 1 quantity squared. So to find intervals of increase, decrease, what we do is f prime of x equals 0 implies f prime of x does not exist implies. So over here, right, a rational expression is equal to 0 when the numerator is equal to 0 and the denominator is not. So that's going to be when x is equal to 0. Really, it's when -2x equals 0, but that's x equals 0. Over here, the derivative does not exist when, again, the only thing that we have is a denominator, so we make the denominator equal to 0, and that's just going to yield x equals plus or minus 1. But we don't really, in doing this, we already know that the derivative is not going to exist there because the original function doesn't even exist at x equals plus or minus 1. So that's not surprising to us right there. So on a sign chart, and when I do a sign chart, even when I have symmetry, I do the whole thing, even though some might say, well, you only needed the positive. That's true, but I like to do the entire thing. So this is my original function, this is my derivative right here. So let me plug in values on these intervals into that. One thing to note with this is the denominator is always positive because I take something and I'm squaring it. So that's always going to be positive. So really, I'm just looking, or I should say non-negative, because it could be 0 at these 2 points. So really, I'm looking at where the numerator is going to be positive or negative, and that's going to give me where f prime will be positive or negative. So if I plug in something like -5 in for x, I have that the numerator is positive 10, and like I said, the denominator is never going to be negative. So a -5 gives a positive derivative, so f is increasing. I plug in something like -1/2. Again, that's positive. This is still positive, so this is positive. F prime is positive, so f is increasing. I plug in something like positive 1/2. When I plug in positive 1/2, then the numerator is negative, denominator is still positive, so this is negative, which means that f is decreasing. And I plug in something like 5, numerator is negative, denominator is still positive, so this whole thing, the derivative is going to be negative, so f will be decreasing. I then have to use this sign chart to create my statement based on intervals of increase, decrease. So I'd say, therefore, f is increasing on the interval from negative infinity to negative 1, union negative 1 to 0, because f prime greater than 0 there. And I'm also going to say, and f is decreasing on 0 to 1, union 1 to infinity, because f prime less than 0 there. Okay, so now I have my intervals of increase, decrease. Using that, this next step, so let me just show you. I'm crossing off the I for intervals of increase, decrease. The L stands for local extrema and the values. So let's go ahead and do that. So this was step I. And step L down here, I'm going to say there exists a local, and now looking at this, right? If f prime goes from increasing and then increasing, there's not going to be a local max or min there. And again, based on the graph, I already know that there's that asymptote there, right? But at x equals 0, the function changes from increasing to decreasing. So that would mean that there exists a local maximum at x equals 0. At x equals 1, again, going from decreasing to decreasing, there's not going to be a local max or min there either. So there exists a local max at x equals 0 because f prime changes from positive to negative there, comma. So f changes from increase to decrease at that point. Okay, but I'm not done with just giving the x value of where there exists a local max. I need to also give the y value. So that's going to be, so the value of that is going to be f of 0, which is, again, I have my original function up here. If I plug in 0 for x, I'm going to get negative 1. So the local max is going to be 0, comma, negative 1. That's where there exists a local max. The negative 1 is the value of that local max. The 0 is where that exists. Okay, perfect. So that's my L. So let's cross that guy out. And so the only other step that I need is the concavity and points of inflection before I go ahead and fully sketch this graph. I do know, right, if I wanted to bring back my graph, I do know now that that is going to be a local max. Okay, so that is a local max, and I know that my function is always increasing from negative infinity to negative 1, and is increasing from negative 1 to 0. And I know my function is decreasing from 0 to 1 and from 1 to infinity. So it's never going to go back up, or there's not going to be some wiggle or anything like that, because I know that the function is strictly increasing on this interval and on that interval, and strictly decreasing on that interval and that interval. So that's what I have so far. Okay? So last step that I need to do is concavity before I finish graphing this. I think I know what's going to happen. I think it's going to be concave up there, and then concave down on this whole thing, and concave up there, but I'm not 100% certain. Another thing I could write down, and I didn't do earlier, was the fact that there is a horizontal asymptote. I should have done this earlier. Horizontal asymptote at y equals 0. So I know that, again, this could drop back down and then come back, but if it dropped back down below it, there would have been an x-intercept, and if it dropped back down below and had to come back up, it would be increasing, which it's not. So it sure looks like it's going to do something like that. And the same is true over here, right? So it sure looks like it's going to do something like that. But we'll draw it perfectly once we go through our last step, which is concavity. So to talk about concavity, we must talk about the second derivative. And we already know, so let me go ahead, I have f of x here. I know that f prime of x was equal to negative 2x over quantity x squared minus 1 squared. And now I'm going to find the derivative of that. So find the second derivative. Well, f double prime of x is equal to, I would choose the quotient rule here, so let's do that. Low d high minus high d low, don't forget the chain rule, all over the square of what's below. Right, x squared minus 1 squared squared is x squared minus 1 to the 4th. And now let's go ahead and do a little bit of simplifying here. So this looks like in the numerator, you know, that minus and that negative, that's just going to be a positive right there. I also see that there's an x squared minus 1 squared, x squared minus 1 to the first. So I can pull out an x squared minus 1 term, and I'm left with negative 2 times quantity x squared minus 1 plus, and if I pulled that guy out, I'm just left with 2x times 2x, so that's 4x squared times 2 is 8x squared. All over x squared minus 1 to the 4th. Okay, I'm still going to simplify in there a little bit, but one thing I noticed is that that x squared minus 1 and one of those x squared minus 1s can cancel out. And so really I'm going to have that f double prime of x is equal to, let's distribute through by that negative 2 up here, so that's negative 2x squared plus 2 plus 8x squared. So it's just going to be 6x squared plus 2 all over x squared minus 1 to the 3rd power. Okay, so that is my second derivative. Now here I have that f double prime of x equals 0 implies that, again, that's true only when the numerator is equal to 0 and the denominator is not. So that's going to be when 6x squared plus 2 equals 0. Well, that's 6x squared equals negative 2, or x squared equals negative 1/3. Well, x squared is never negative, so this is going to be never. Right? Over here, seeing where f double prime of x does not exist, this is going to be, well, this only doesn't exist when the denominator is equal to 0, and we've already seen that where x equals plus or minus 1. And again, that's not surprising. The original function didn't exist at those values, and the derivative doesn't exist at those values, so the second derivative is not going to exist at those values either. Now that I have those values, I'm going to put that on the sign chart and check values on the intervals into the second derivative. So when I plug in something like negative 2 in for the x for the second derivative, well, do you see that the numerator is always going to be positive here? Because I'm taking something, I'm squaring it, I'm multiplying by 6, that keeps it positive, and I'm adding 2. So numerator is always positive. So really I'm only checking out, plugging in values into the denominator to see whether that makes this whole expression positive or negative. So when I plug in negative 2, that gives me negative 2 squared is 4, minus 1 is 3, cubed, that's positive. A positive over positive is positive, so f is going to be concave up. When I plug in something on this interval, like 0, numerator is still positive, denominator is now negative, right? 0 squared is 0, minus 1 is negative 1, cubed is negative 1, so f double prime is negative there, so f is going to be concave down on that interval. I plug in something greater than 1, like 5, positive, positive, everything's positive for the second derivative. which means that f is going to be concave up. Again, I need therefore. F is concave up on the intervals from negative infinity to negative 1, union 1 to infinity, because f double prime is greater than 0 there. I also have that f is concave down on the interval from negative 1 to 1, because f double prime is less than 0 there. Okay, so those are my intervals of concavity. But with this, C is also going to be your points of inflection. So let's look at it. At negative 1, the second derivative changes sign, or the original function changes concavity there. However, what I already know from the domain, or just trying to plug in negative 1 into the original function, the function is not going to exist there. I'm not going to be able to have a point there because the function doesn't even exist. So there cannot be a point of inflection at x equals negative 1. It was a possible point of inflection due to this sign chart, yet I definitely see that there will not be a point of inflection there because the function doesn't even exist there, and the same is true at x equals 1. So I'm going to say also in here, there are no points of inflection, just to make sure that that is stated as well. Okay, so now I have that, and I have verified what I thought was going to be true based on concavity. Let's go ahead and sketch this graph all the way through. So now I know that this is where the derivative was equal to 0, and I definitely have that the function is concave down on this interval, so it's going to go something like this, derivative 0, right, something like that. And then over here, let's just make this look a little bit nicer, but again, the function's concave up here, and I have my horizontal asymptote over here, and I have my vertical asymptote and how it approaches it up there, and then I have the same thing over here. That's already graphed pretty nicely. So this is your graph, right? We go through and we would have to label everything. Label all of, so the thing, I label this a local max, I did not label that as the y-intercept. So I'm going to say y-intercept and local max. So we have to label all intercepts, we have to label all asymptotes, those are already labeled for me. We have to label all local extrema, and all points of inflection. All of that is done. There are no points of inflection. I have my local max right there, and so I'm done. Okay? So that was using the steps learned in class, namely domain, intercepts, symmetry, asymptotes, intervals of increase, decrease, local extrema, and the values, concavity and points of inflection, and then sketching the curve. Okay? I hope that's helpful.